Good evening and welcome to the live sessions. It is 6 p.m., but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you. Good evening, and welcome to the live sessions for the course on Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajan Kapil, who is a member of the faculty at the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Uh, Over the past couple of weeks, we have looked at additive manufacturing processes that primarily utilized liquid as the feedstock material, such as VAT photopolymerization, digital light processing, and similar. This week we'll be looking at additive processes that use sheet as the raw feedstock. We know that ASTM classifies the additive processes differently into seven broad categories. But for the purpose of this course, we're looking at them in the purview of the type of feedstock used. One point which we also discussed when we were discussing the fundamentals of additive processes is that inherently all sheet-based additive manufacturing processes are hybrid in nature, and we'll be looking into why that is today. So in this first set of slides, we'll be going over cubic technologies, laminated object manufacturing. ERA's paper lamination technology, solid dimensions, plastic sheet lamination, CAMLAB, and NX corporation's offset fibers. Just like all our previously studied additive processes, here again we have divided any technology into its various subsystems, which makes classification far easier and systematic. Again, as you would see, the presence of this sub-block of cutting methods is very interesting because this is perhaps the first time that you are seeing it. Regardless, the type of materials that we are dealing with are paper, plastic, ceramic, and metal. We have two approaches, being bond then form and form then bond. We'll be discussing what they mean. For cutting, laser, knife, a milling cutter, or what it may be used. Bonding between the various sheets of the additive feedstock may be achieved using conventional adhesive by a sintering cycle, by diffusion, such as in diffusion couples, or spot welding, or a soldering or brazing like process may be used. Next, the regions that we join via these bonding methods can be the entire feedstock for the particular layer, from which we then separate out the useful regions, or it can be selective to begin with. Of course, we talked about the form and then bond and then form approaches. But how do they typically differ? On the right here, we have a schematic which discusses the two of them. The square, or okay, better to say rectangular sheet that we see here is the feedstock in yellow. And out of that, a shape is being cut which is the shape of a star. In the form and then bond approach, we first cut out this useful region or region of interest from the feedstock and then assimilate it with the existing or pre-deposited or pre-joined layers. So we will cut this and transport it here on top, and then using some mechanism or some adhesive like we discussed, it will be stuck to the pre-deposited layers. The other approach, which is bond and then form, is different because here we are attaching the entire say sheet of paper or sheet of metallic sheet to the previously deposited layers, where we again see that the same square or rectangular region is present. The entire new sheet is adhered to it, and then the useful region is cut out. We also see these fine grid lines on the outside with the label of decubing. We'll be discussing what it means. In the form and bond approach, handling the cut pieces may be difficult because often the shapes are uh, intricate. Again, per layer, there may be more than a single contour which has to be, say, taken out. There may be additional contours in addition to the single one that is shown here. And handling multiple such contours per layer may be a challenging task. The pieces themselves may be odd shape and may not be self-supporting. Uh, if it is used with a paper feedstock, then paper being flexible will again complicate handling. It can bend or creases can form. And a support mechanism will be required in case we have overhangs between a layer and the next. In the other approach, which is the bond and then form approach, handling is comparatively easy because what you're essentially doing is just stacking, say, one rectangle on top of another. Indexing of the reel is all that is required. The pre-existing deposited material or the existing stock acts as the support material in case any overhanging features are to be generated. The decubing process, however, which is where we remove all of this excess material that we have been adding per layer, removing that will take a considerable amount of time, and as you will see, it is in fact the rate determining step for this process because it is the slowest and it is well adapted for the use with feedstocks such as paper, which are flexible in nature. For the first technology, which is cubic technologies laminated object manufacturing, the feedstock material that is used is a paper. The approach used is bond and then form. We will bond the entire new, say, rectangular region of paper onto the existing deposit and then cut the useful shape out of it. The cutting method for cutting out these contours is by the use of a laser. Bonding method by which the new sheet of paper is joined to the pre-existing deposit is using some suitable adhesive, and the joining region will be the entirety of the rectangular region in the present layer. The laminated object manufacturing process is an automated fabrication method in which a 3D object is constructed from a solid CAD representation by sequentially laminating the part cross sections. So yeah, just like any other additive process, except here we are laminating the cross section in each layer. And just like all other additive processes, there are three main phases, those being pre-processing, the actual build cycle itself, and post-process, which, as we will see in this case, takes the longest amount of time. The pre-processing method across most additive processes is almost uniform, where we have the preparation of the CAD file and its conversion to an STL file. If we are going through the indirect slicing route, just to jog our memories, we can also go via the direct slicing route, where we do not really approximate the geometry given to us. We treat it exactly, that is, we use mathematical curves to define the geometry which is given to us, thereby preserving all intricate features, curvatures, and other aspects. And we can slice it directly for this method, for this technology, typically using planar layers. Thus, in every slice, the contour that we end up with is an exact representation of the original geometry from which it is derived. A second way, which is of course far more commonly used and seen in commercialized additive manufacturing technologies, is the intermediate conversion of that exact geometry to an STL file, which is easier to handle, easier to manipulate, has well-defined methods for, say, finding and calculating support structures, and is very well adapted and researched. And then, when we slice such an approximated geometry from the original geometry, in each layer, the contours that we'll end up with will not be smooth curves, but rather some approximated curve in the form of a multi-sided polygon. Then, this converted or exact geometry is positioned and oriented in the desired place. Of course, good practice is to tilt it by 10 to 15 degrees to avoid any surfaces being horizontal. The reason it is done is we did discuss it in one of the previous sessions where we saw that we want to minimize the number of horizontal surfaces. The reason being, as we know that horizontal surfaces, say if unsupported, will act as overhang and will require support structures. These support structures, in some cases, may subtend all the way to the build plate or substrate, but in some cases may fall on the part being built itself. Irrespective, and however careful we are with the removal of these support structures, and they always tend to leave remnants on the final built part, which affects the build quality, the surface finish, and the desired properties of the part. So, a good practice is to minimize the number of horizontal surfaces. The CAD model is then sliced, and the contours, both interior and exterior, are obtained. And some of the useful process parameters for this LOM machine are the diameter of the laser beam, whether you want to use, say, different diameters of beams for cutting out different contours. For instance, for the exterior contour, we can use a fine laser beam so that we have a precise cut, whereas just for the decubing grids shown here, we can actually use coarse or a larger size of beam die, because now we are just concerned with removing the material. We are not really concerned with a lot of geometric accuracy. With the beam offset flag, because the beam die itself will have some finite dimension, and if we are very tight on tolerances, we would actually want to offset the beam by half its beam dia so that the cut dimension is exact. Grid sizes for normal and fine grid cutting. You would can work with larger grid sizes, say far away from the contours, but near the contour, the grid size might have to be refined. Of course, whenever we talk about such a refinement step, it's always an interplay between time and accuracy. So it's not like we can arbitrarily refine the grid, and it will take a very long time to remove all of that excess material. On the other hand, if we have a very coarse grid throughout, the geometry that we're trying to capture may not be represented well. So it's always a compromise between time and accuracy, and adaptive machine is the way. The number of dummy layers, because typically in laminated object manufacturing processes, we would paste a few layers of sheet on the substrate, which can act as sacrificial material and can ensure a good adherence and good adhesion of the successive layers. In the case of, say, fused deposition modeling, as some of us might have already seen, even your typical stationary glue or fevigum is used to stick, is pasted on, used on the build plate to ensure that the first layer uh, adheres well and sticks well, bridging gaps between the two builds and so on. Now, a schematic of the machine is presented here on the right. We see that there are two roles, one being the material supply role, one being the material take-up role. The take-up role need not exist in all such processes. but it does exist in cubic technologies long. The material, as we already know, is available in the form of a sheet, and it is rolled over this region where the printing happens. There is this laminating roller. In fact, there may be a pair of such rollers which uh, rotates and goes over this region of interest. By the action of this roller, the new sheet of material is stuck to the pre-deposited layers. Either it can use some normal force in the case of some thermally activated glue, or it can use heat in the case of sorry, it can use normal force in the case of force activated glue, or it can use some heat in the case of thermally activated glue, or typically it would be a combination of both. We have a laser system and some optics. As we discussed last week, typically this will just be a galvanometer, which is a pair of mirrors which are mounted onto two motors, which are very agile and can swiftly, say, scan or project the laser beam all over the printable area. We have the laser outline and crosshatch. We have this, say, outer rectangle, which denotes the overall printing area in a region and which defines the cubical or cuboidal geometry of the final block which will be printed. And inside, we also have this region marked in red, which is the actual geometry needed. We see the pre-deposited layers in the form of this part block and the platform, which will go up and come down suitably between different layers. So during the building phase, thin layers of adhesive coated material. This coating will typically be, say, on the underside, are sequentially bonded to each other and individually cut by a CO2 laser beam. Remember that in this case, the feedstock material is typically paper, and so CO2 laser beam is, uh, say, good enough to cut it out. In fact, CO2 laser beam also has a couple of other advantages, such as its cost effectiveness and ready availability, and its good interaction with paper. We have also discussed how the wavelength of the energy source is a very important parameter in deciding its interaction with a given material. Wavelengths of certain wavelengths may be suitable for metals, whereas others may be suitable for ceramics. CO2 lasers, in fact, are also suitable for ceramics, apart from paper. And even in the case of metals, the absorptivity of the irradiation source itself may vary with wavelength. For instance, uh, the typical so-called red lasers, which are some 976 to 1000 nanometer in wavelength, which interact well enough with, uh, say, iron-based, nickel-based, or titanium-based alloys, fail to print or deposit aluminum and copper-based alloys satisfactorily. However, lasers of considerably shorter wavelength, such as blue lasers and green lasers, do the job really well. In this case, the CO2 laser beam is seen to be effective in cutting and joining this paper. The paper is indexes by a fixed distance and it has adhesive at the bottom surface. In each layer, the table rises to the required height. A hot roller, which is the laminating tool, rolls over it, causing the paper in the current layer to stick to the previous layers. The height which is thus achieved is measured and passed on to the slicing software in case any adjustments have to be made. The loops of the slice are cut by the laser. It is possible to offset the laser beam by the beam radius um, in such a direction as to compensate for it, which is the point that we have already discussed. This is followed by grid cutting around the bounding box. So the rectangular box that we see on the outside is actually called the bounding box of the stock. The grids of all the layers coincide, and this is just to have, ease of removal later when we are getting rid of all the excess material during the decubing process. Finally, a parting off cut is made when this material is parted off, and the table can go down, and the next layer of this sheet feedstock can come on. Much simplified schematic is also present in this layer, where we see the cycles between the coming of a new layer, its adhesion with the previous deposited layers or the bonding process, and the cutting of the desired shape in the present layer. Now, as we have been discussing, it is actually the post-processing step which takes the longest amount of time in cubic technologies long. Once all the layers are made, the final built volume that we end up with is just a cuboidal block. This is parted off from the table using a thin wire rope. Typically, in the case of parts printed off metal, they will be separated from the build plate using wire EDM or an abrasive cutting process. The unwanted material inside and surrounding the built part are removed using hand tools. This process is called decubing, and this operation can take several hours. Not just that, it requires, say, skilled labor and a lot of man hours. And here we can see that the operator is removing it using some chisel and other hand tools, uh, layer by layer, at the same time taking great care not to damage the built part. The part is finished and may also further be painted as required. It can be given a lacquer coat to prevent it from absorbing moisture because the part is made out of paper after all. This process offers several advantages, such as that only boundaries or the contours are to be traced and not the interiors. Typically, in all other additive processes, such as last week we were discussing VAT photopolymerization, there was a lot of stress on how the laser scans the interior or the area filling of the region which is to be deposited. How much depth is useful? Can we go very fast? What is the curing depth? What is the ultimate depth? What should the overlap? What should the step over, and so on, just to ensure that within the region that we wish to deposit, the curing is satisfactory, the material gets deposited well, and the part has good strength and no voids. Here, we get rid of all of that because what we're essentially doing is just cutting the contours. Therefore, the process is very fast. Since in this case, the speed is only proportional to the surface area of the object. We are just in each slice, we are only scanning the exterior contour or the interior contours, and you stack it over the 3D build. What you have essentially scanned is just the surface of the build. Whereas in other cases, we scan the infill regions, and so when you stack it across several layers, what you have essentially ended up doing is scan through the volume of the part. Since this process only is proportional to the surface area, it is considerably faster. It uses carbon dioxide or CO2 laser, which is cheaper and more readily available. Also, this laser is used only for cutting operation, and hence the control is simpler than for curing or sintering. No protective environment as such is required. However, proper exhaust is required to take away the fumes or smoke which may be generated in the process. Paper is as a feedstock is cheap, considerably cheaper than say metal powders or even resins or filament. The end parts which get printed are strong and they are wood-like, and these work as very ideal patterns for casting. And Professor Kapil has given this beautiful analogy here, where he says that typically paper is made out of wood pulp. In this case, using paper, we are making parts that are as strong as wood. So, in essence, we are making wood out of paper. And these long concepts are used in laminator tooling and manufacture as well, as we'll see in one of the later examples. However, not all is rosy, and there are several disadvantages to this process. First is the lack of adaptive layer thickness. The layer thickness in this case is fixed, and this is also equal to the thickness of feedstock or the sheet thickness. And thus, adaptive slicing is just not possible. The decubing or grid cutting process, which is a post-processing step, takes far more time than object cutting. And we'll also solve a numerical using some standard values to see what is the exact scale of the grid cutting or decubing time to the object cutting time. Sorry, this is just grid cutting, which is scanning of the unused or non-interest regions in each layer. Decubing, which is the removal of all such regions or the volumes at the end of the printing process, is even more time consuming. Horizontal surfaces will pose problems, and since we are using a paper feedstock, of course, the entire process is highly prone to fire accidents. Lastly, the reason it is not commercialized and it is not very frequently encountered, say as frequently as your FDM or even metal 3D printing or wet photopolymerization, is because of poor product development, non-existent marketing, and hence the technology is almost dead. Here we have an example of a part which was built using this LOM process. It is the model of a crankshaft with an actual length of approximately 40 centimeters. The next technology, which is very similar to Cubic Technologies LOM, is Kira's paper lamination technology, which, as the name again implies, uses paper as the feedstock material. The approach is bond and then form. Cutting and separation is performed using a mechanical knife. The bonding method remains an adhesive, and the joining region is again entire. So the only change from cubic technologies LOM being the use of a mechanical knife instead of a laser, and we end up with the Kira's paper lamination technology. So in principle, it is same as Cubic's LOM. A blade or a knife is used for cutting instead of the CO2 laser. And what this means is that, say, previously in a layer, if, if this was my contour and I was scanning it using a laser, it did not really matter whether I went clockwise or anti-clockwise. Whether I scanned till half and then suddenly switched to some other region and continued scanning from there. All I had to do was just scan over this perimeter any way I liked. Now, when I try to do the same thing with mechanical knife, so typically this knife will have only one sharp edge. Even if we have two sharp edges, there is still this lateral face which will be blunt. And so I cannot just scan along any direction I feel like. I have to scan only along the direction along which the blade is sharp. So what I'm giving up on is actually omnidirectionality. The process overall is very similar to a laser printer, and here the toner is used as the binding agent. Lamination is done by a hot plate in this case, rather than a hot roller, and as we'll see, it offers certain advantages. Because of the use of a plate, which affects this lamination over the entire surface area at once, the pressing is more uniform, and the layers do not slip due to the sort of shear which occurs during rolling. And therefore, also one of the previous names for this process was actually selective adhesive and hot press or SAHP. Typically, the part sizes are smaller than cubic slump, but then they are also more accurate. Only one roller is used instead of two, as in cubic slump. And since there's only one roller, we can by default know that it is the material supply role rather than the uh, take-up role. In this case, the pre-processing steps are same as cubic lump, plus the preparation of the machine by pasting few buffer layers. I think Professor Kapil also showed a video where this process was shown, where the first few layers are stuck using adhesive glue. So these were actually stuck using some adhesive glue. And then the process itself was started. During the build, a sheet alignment mechanism adjusts the printed sheet of paper onto the previous layer on the model. The first layer starts from the table itself. A hot press or the hot plate then moves over the sheets with the printed sheet pressed to the hot plate at high pressures. The temperature controlled hot press melts the toner, which is actually resin powder, and the paper then adheres to the sheets together. The hot press also flattens the top surface and prevents the formation of air bubbles between the sheets, which might have been a possibility during the use of a roller. The PC measures the amount of movement up to the hot plate to compensate for any deviations of the sheet thickness. The computer then generates plotting data based on the section data of the model. A mechanical cutter, which we know is just the knife, cuts the top layer of the block along the contour of the section as well as the parting lines from which the excess paper are removed later. These steps are removed until the entire model is built. Since in this case we are using a mechanical cutter and also a bond and then form approach, we must be very careful of the depth of cut that we are taking, because the pre-built layers are also existing below the layer which is currently being built. If the depth of cut is too high, then we risk damaging those layers which are already built. On the other hand, if the depth of cut is too low, the separation of the current layer, uh, the unnecessary region of the current layers will be difficult and it will leave some remnants. So the depth of cut has to be controlled very tightly. The post process is same as cubic slump, which requires decubing. Here we also have a very helpful schematic of the process, where we see how we have a paper roll which is feeding uh, the paper feedstock. Then the cutter plotter will cut the required region of paper, and the heating plate will uh, bond it onto the pre-built layers, and onto this new sheet of paper the cutting now will plot the required regions. And here we have a short snippet which shows how the decubing step takes place. And on the top surface, we'll also see all of these grid lines. The advantages of Kira's paper lamination technology are that it uses a flat plate and high pressure to bond the layers together. Also, there is the effect of heat. Each layer is pressed with a flat hot plate, and the model remains flat during the entire build process. Since the block is released after cooling, there is minimal internal strain in this case, and therefore there is little or no curling in the final model, so there are no distortions. Uses a computerized knife to cut sheets of paper, which results in a smooth surface for the built model. Since only a mechanical knife is used instead of, say, a laser, which may lead to burning or a lot of heat generation, there are no fire issues, and neither are there any hazards per se, which are common to laser cutting. Because of the use of mechanical knife, even the emission of smoke and fumes will be very low, if at all. The high lamination pressure used in this paper lamination technology process has resulted in products that are 25% harder than equivalent wood. In the previous case, we saw that uh, the parts had strength equal to wood. Here they are 25% harder, and the parts it built are often strong enough for most prototyping applications, including sand casting. So perhaps the built parts will have more actual applicability than those built out of just cubic technologies alone. Other advantages are similar to top. Again, some of the disadvantages are the fixed layer thickness and the lack of adaptive slicing. Grid cutting, as usual, taking much more time than object cutting. Decubing being the rate determining step. Horizontal surfaces being problematic in general. The next process using uh, plastic as the material in this case is uh, solid dimensions, plastic sheet lamination, where the feedstock is plastic. The approach remains bond and form. Cutting is done again using a knife. Bonding method uses an adhesive, but in this case, the joining happens over a selective region. It uses a thermoplastic, which is a transparent material as the raw material, and thus the process is suitable for making transparent parts. The adhesive, together with the selectively applied release agent or the masking agent, is used for binding the sheets. And a support removal method called peel away is used, which is easier than the decubing method. And okay, here we also have the process cycle for this, where we have the preparation of the STL file, preparing the toolpath for cutting, gluing and the release agent, the preparation of the machine by pasting first few buffer layer, and so on. Here we saw that there are two things. One is the adhesive itself, and then there is this masking agent or release agent. So what essentially happens is that, say, between one layer and the next, say if this is my useful contour, and all of these regions in yellow are essentially have to be removed away. They're not part of the final build. Here I will just uh, say bond together the regions of interest, which are these two regions. And the way it is accomplished is by using uh, this release agent or the masking agent over all of the yellow regions. A beautiful analogy of this adhesive and release agent or masking agent given by Professor Kapil is that of water and adhesive tape. So if you have sellotape or scotch tape at home, the adhesive on the adhesive tape is the analogy. And for the masking agent, we have water. If ever while playing with scotch tape, we have put a few drops of water on the scotch tape, then we see that the regions with water will not really stick, whereas the other regions, because of the action of the glue, will stick to some surface. Here, the regions which are not desired to be joined together and are effectively to be removed are covered with this masking agent, whereas adhesive is only activated in regions which are desirable. And to remove all of these undesirable regions, we have some uh, we have this method of peel away, where successively for each layer, uh, So they will be joined at few points. And finally, across the layers, we'll have, say, all of them joined together. And finally, we will just pull it from this end so that all of this will get peeled off. The post-process step in this case is just the peel away, which takes far less time than decubing. A video was also shown during the lecture, which illustrated this process. The next process is CAMLEMS CL, which processes ceramic materials, uses a form and then bond approach. The cutting method, because of the use of ceramic, is laser. Bonding method is via sintering, and the joining region again is entire. The process itself stands for computer-aided manufacturing of laminated engineering materials, and as we discussed, it uses the form and then bond approach. Uh, just like a typical additive process, we start from a solid CAD model, get the contours for each layer, and then for each slice, we print the green object. In the parlance of, say, sintering, we know that a green object is just a cold pressed uh, or a raw object which has not been sintered yet, and thus it has a very poor mechanical strength. It can easily break or deform. Uh, each layer of this green object is cut using the precise laser, and then based on some reference points, such as these holes here and the corresponding, say, poles which match up with these holes, we have to stack them up. Once stacked, these go into a hot isostatic pressing type of process where they get laminated. And during the sintering process, the binder, which was, say, bonding all of these layers together, gets removed or burnt off, and uh, the parts joined together by sintering, and we end up with a finished component. In fact, a variety of materials can be processed in this machine, ranging from ceramics to metals. Up to 5 materials can be used in a single machine, and this truly gives us the capability for multi-material 3D printing. And some typical build volume sizes are given here, and the layer size, as we can see, is between 100 to 600 microns, which is not the finest resolution you can get, but still good enough. Here, the advantages are that internal channels are possible, but then they're possible in other additive processes as well. Maybe not so easy in laminated sheet object or laminated object manufacturing type processes, and so it's mentioned here separately. Since it's a form and then bond approach, so no precise depth of cut is needed. Say typically here, there will be some sacrificial plate at the bottom, and even if we use, say, a much higher depth of cut for the laser, and we end up cutting some of the plate, it does not really matter because it is of a sacrificial nature. Had this already been pasted on the pre-deposited material, then we would have been in trouble because then we would have to be very precise with the depth of cut that we are taking, but not so in this case. There is no unwanted glue material because whatever binder uh, was present gets burnt off during the sintering process, and variable materials and layer thicknesses are possible depending on the layer that you're taking in each case. There are several disadvantages, however, those being of shrinkage, since this is a sintering process, and we know that typically, say, we'll start with some shrinkage allowance, maybe say 5% is a typical number. We'll start with a 105% volume of our material, expecting a 5% shrinkage, after which the final geometry will be exact. Precise alignment is needed, which in this case was ensured through the use of these, say, placement holes and corresponding poles for alignment. And there's a lack of support structures, so if there are overhangs, they're not really supported. It totally depends on the green strength of the part. Then there's this process of offset fibers by NX Corporation. Here again, the material is paper. The form then bond approach is used. The cutting method uses a mechanical knife. The bonding method uses adhesives, and the entire region is joined. It is also similar to Kira's paper lamination technology. The main difference being that offset fabbing uses the form and then bond method compared to the bond and then form used by Kira's paper lamination technology. Uses a mechanical knife to cut the outline of the layer, and after that, the sheet of the material is cut to the required shape. It is transferred using this carrier plate, as we see here, onto the pre-deposited layers. The carrier beaded material is also shown here, which is the material which will be removed and is not really part of the build. It uses a mechanical knife to cut the outline of the layer after the sheet of the material is cut to the required shape, which is then transferred and laminated onto the previous layer. And the process of cutting and laminating of the materials is repeated until the whole model is built layer by layer. Here again, despite using a cutting knife, we must be very careful with the depths of cut that we're taking, because the carrier plate might end up getting damaged, which is undesirable because it will not be replaceable. In fabrication materials, such as any thin film that can be cut and bonded to itself by means of some adhesive, is rested on the carrier plate. A two-dimensional plotting knife is used to cut the outlines of cross sections of the desired object into the fabrication material without cutting through the carrier, as we were just discussing. The plotter can also cut parting lines and outlines for support structure. However, we do not have, say, adaptive cutting, which was possible for the case of lasers, where we use, say, a finer beam dia for cutting the actual part contours, and a coarser beam dia for cutting the grid lines. The film is then weeded to remove some or all of the negative material. As we know, weeding is the process of removal of unwanted material. The film is inverted so that the carrier is facing up and the cut pattern is brought into contact with the top of the gluing object and bonded. This carrier is then peeled off to reveal the new layer. Some of the advantages are its applicability to a wide variety of materials and minimal shrinkage compared to, say, CAMLM. And the disadvantages include again the need for precise cutting force and precise depth of cut to prevent any damage to the build carrier plate, the need for precise alignment across layers, and the large usage of materials. But then that is true for any laminated object manufacturing process. The last two processes that we'll be looking at before wrapping this up are the ultrasonic consolidation and the laminated manufacturing processes. Ultrasonic consolidation, which uses metal, which as say students of mechanical engineering, we are primarily interested in, uses a bond and then form approach. The cutting method for removal of the excess material in each step will be milling. The bonding method for joining of these metallic sheets would be by diffusion, and in each layer only some selective region is joined rather than joining the entire sheet. Ultrasonic consolidation is a hybrid additive subtractive method based on the ultrasonic metal welding of a sequence of metal foils with in situ material removal process through a 3-axis CNC contour milling. Due to moderate applied pressures and relatively low temperatures experienced by the sample, it operates as a solid state process, which is very important because, as we know, that for solid state processes, since the material is not really undergoing the melting and solidification cycle, the residual stresses or internal stresses are minimal, and hence any dangers which are posed by the presence of residual stresses such as cracking or warping are automatically rid of. It works on the principle of bond and then form approach, and the process was invented and patented by Solidica in 1999. Later, Solidica collaborated with Edison Welding Institute in 2011 to start the company called Fabrisonic, which is the manufacturer of ultrasonic consolidation machines. Uh, this slide describes the typical working of such a process and what it is made out of. So it will be plugged in into a regular 50 kilohertz power supply, but then through some means we convert it into this ultrasonic frequency, which is 20 kilohertz. Uh, this electrical energy is then converted into the mechanical energy through an actuating transducer shown here in red. A booster is attached sequentially to say boost the amplitudes of this transducer, and finally they are transmitted to the sonotrode, which passes on these ultrasonic vibrations to the welding piece. Under a compressive normal force, and on the right also we see a three-dimensional view of the same, where we have the welding speed, which is the speed with which the roller is moving along this direction. We have the transducer, which converts the electrical energy into mechanical vibrations. We have the booster, which increases the amplitude of these ultrasonic vibrations, and then the sonotrode, which actually say through which these ultrasonic vibrations travel into the workpiece. The welding force is the normal force applied to the sheet. We see these previously bonded films and the anvil and base plate. Also, we see that the direction of this ultrasonic oscillation or ultrasonic vibration is actually, say, orthogonal to the welding direction. They're not in the same direction. In each layer, a thin metal foil, which is approximately 100 to 150 micrometers thick and approximately 25 mm wide, is placed on a sacrificial base plate that is bolted onto an anvil. Why bolted? Because they will be subjected to these ultrasonic vibrations, which can cause the anvil to come loose and the printing process to be disrupted. So they have to be bolted. The foil is compressed under moderate pressure by a sonotrode, which vibrates nominally at 20 kilohertz with a peak-to-peak amplitude that ranges between 5 to 40 micrometers in the transverse direction. The sonotrode has a roughened surface. Typically, this is introduced by, say, knurling. And the reason for this roughened surface is to grip the top surface of the foil, vibrating it without slip. This causes relative motion between the foil and the base plate. Performing this process at room temperature produces heat through the scrubbing of the meeting surfaces at the bonding interface. The heat causes the temperature rise, that is between 30 to 50% of the base metal's melting temperature. And since we are not really going close to the melting temperature itself, it's a solid state process. Typically, you would also preheat the build plate, and it is conducted at approximately 200 degrees Celsius by employing a heated base plate. And once a layer is bonded, additional layers are also added and machined. The process is then repeated until the desired dimensions of the features are reached. And in the schematic here to the right, we also see the excess material removal step, which occurs through this CNC milling contour cutter. This will get rid of, for example, all of this material in between, which is not needed in this case. We'll also dive a little into the fundamentals and the working principle of this technology. The ultrasonic consolidation process itself lies somewhere between solid state diffusion bonding and linear friction welding. And let us see how that is so. In solid state diffusion bonding, there is no scrubbing. of the two surfaces and essentially no relative motion. Diffusion bonding relies on elevated temperatures between 50 to 90% of the melting point and high pressures to flatten the bonding surfaces, fragment impurities, and produce atom to atom contact. Because, as we know, for say any surface, no matter how precisely we machine it, it will never be atomically smooth. There will always be some undulations, which are called as asperities. And further, there will be some oxide and contaminant layer formed on the uh, outer periphery of these surfaces. Thus, large pressures must be applied to break up these impurities, to flatten these surfaces and the asperities, and to make sure that the two surfaces are coming in atom to atom contact. When the surfaces are pressed together at high pressures, atoms will diffuse along the grain boundaries, closing voids in the contacting surfaces. The atoms condense and further reduce the size of any voids in the interface. Such a pressure can be applied for few minutes, up to few hours, or even weeks or months, depending on the material being bonded, the extent of diffusion that we're looking for, the temperatures and pressures that we're working with, or our objective in general. Since there is no relative motion, the dependence on interfacial motion is low. Contrast this with friction welding, where the bonding is solely and entirely dependent on pressure and frictional scrubbing at the interface. Here, the process itself begins with two pieces that are statically clamped. Then, depending on the process, inertia welding or linear welding. In inertia welding, the parts are rotated, and in linear welding, the parts undergo linear reciprocal motion. The pieces are brought together under light pressure, causing frictional heating. Finally, a forging pressure is applied, and the relative moment is stopped to form the final joint. The stress on the material due to the scrubbing and forging causes the material to reach plastic state, which helps remove surface impurities. After the plastic state has been reached, the two surfaces are forged together. Here, because it relies entirely on relative motion and scrubbing at the interface, the dependence on interfacial motion is high. Ultrasonic consolidation shares many aspects of both the joining processes. It is performed at an elevated temperature between 30 to 50% of the melting point, similar to but lower than diffusion bonding, and the interfacial motion of friction welding process. It is unique in the sense that ultrasonic waves travel through the bonding metals, lowering the modulus and the stress needed to reach a plastic state. This effect, where the ultrasonic waves travel through the bonding metals and lower the modulus and the stress needed to reach plastic state, is called acoustic softening or the Blaha effect. In fact, experiments have shown that the use of ultrasound in diffusion welding in an inert gas atmosphere or vacuum reduces the time needed for bonding. The mechanism of bond formation during ultrasonic welding of metals has been widely studied, but the exact workings are still not known. There are several theories about the physics that govern this process. One of them is discussed here. When two relatively flat surfaces are brought together, only the peaks of the surface asperities actually touch. So, as I was saying, uh, no surface will be atomically smooth, and at the microscopic or even nanoscopic level, what we'll actually end up seeing is there are several hills and valleys, These hills are called asperities, also shown here. Thus, when we are bringing these two surfaces in contact, it's just the asperities of the two surfaces which are coming in contact. Thus, the apparent area of contact is equal to the geometric area of contact, whereas the actual area of contact is just a tiny fraction of it. The physical contact area is much less than the geometric area of contact, and ultrasonic consolidation causes the physical area or the actual area of contact to approach the geometric area of contact under the application of normal loads, and these transfers ultrasonic vibrations. Ultrasonic motion causes the oxides to break up via the process of acoustic softening, allowing direct contact of pure metal, resulting in metallic bonding. The bonds themselves are in turn plastically deformed by shear vibrations, resulting in heat, which promotes diffusion and crystallization of material between the layers, resulting in a true metallurgical bond. In addition, the process is aided by the transfer of ultrasonic energy into the metal, which acts similarly to localized heating, thereby reducing the stress needed for plasticity. And the way ultrasonic motion affects the breakup of these oxides to reveal the metallurgically pure metallic surface is by shifting the curve by reducing both the amount of heat and the amount of stress needed to reach the plastic stress state. This is known as Blaha effect or acoustic softening, as we have discussed. Here we have a useful schematic of the process. Here we see how on the face of the sonotrode we have these rough patterns which have been knurled onto the surface. This knurl pattern is actually a necessary evil. On the one hand, it is necessary to prevent any relative motion between, say, the foil in the present layer and the sonotrode, because if there is relative motion, then the sheet can get deformed. The oxide layers between this present sheet and the pre-deposit material will not break up properly. Bubbles can get trapped, air can get trapped, and porosities can form. And so it is very important for the sonotrode to grip the sheet adequately. Uh, the vibrations occur at very high frequencies, as we just saw, typically 20 kilohertz, which may not even be perceptible by the human eye. And so we have to ensure that this contact is very strong. On the other hand, if the knurl pattern is very deep or it is unsuitable in any way, these patterns will transfer onto the sheet metal and it will stay there in the finished part. Now imagine you have such a knurl pattern on the sheet metal between two layers. It will lead to interlayer porosities, or these can act as sites for contamination or cracks or other defects in general. So while the knurl patterns are important, we should ensure that they are not too deep, or the normal force which is being used for the welding process is not too high, else they may get transferred onto the built part. Of course, they will also destroy the surface integrity of the part. There are several process parameters in the ultrasonic consolidation process which have to be carefully tuned in order to achieve the desirable build quality. Some of them are listed here. The travel speed of the sonotrode determines the energy exposed per unit length of the welded track. Those of us who are working or have studied additive manufacturing know that the energy density is a very important aspect that controls the microstructure, the strength, the properties, and the presence of any defects in the built part. When comparing across processes or when comparing parts built for the same process, we would of course take great care to mention the energy density that was used, because it is in many ways decisive of the characteristics of the part. Thus, we have to ensure that the travel speed is well controlled and consistent to ensure consistent energy deposition for energy exposed per unit length of the weld track. The amplitude of vibration is important because it directly correlates with some other characteristics. Higher the vibration amplitude, the greater the ultrasonic energy which is transmitted to the material. A sufficient amount of ultrasonic energy is required to plastically deform the material and fill the voids at the interface of the sheets. If this, if the amplitudes are too small, uh, the welding effect will be very weak, and we can have this interlayer voids. On the other hand, if the amount of energy is very high and exceeds some critical level, the excess plastic deformation may damage the previously formed bonds at the interface, which is again not desirable. The normal load that we use during this process flattens the asperities and determines the magnitude of the limiting value of friction force, and thus the stresses at the interface. A sufficient amount of such normal force ensures metallurgical bonding across the interface. However, if the normal load exceeds a critical level, the excess plastic deformation may damage previously formed bonds at the interface in a manner similar to the amplitude of vibration. The temperature of base plate and any external heat which is provided could serve to reduce the apparent stress for plasticity. It can enhance atomic diffusion, it can reduce strain hardening due to plasticity, and can have other beneficial effects. That is why, as we saw, typically we'll be working with preheated base plate, which is heated to approximately 200 degrees Celsius. The texture of the sonotrode or the knurling pattern which is delivered to the sonotrode directly affects the amount of damage to the surface of the bonding strip. Excessive damage may lead to large gaps in the bonding interface, and in addition, it affects the gripping inches of the sonotrode on the strip's top surface. Ideally, the texture would grip the strip so that no differential motion or no relative motion exists at the strip sonotrode interface. The electrical power draw, which is a measurable quantity and which can be studied to actually find in-process insights, may reflect the different conditions of stick and slip at the interface. One can easily see that the sonotrode requires more power to counteract static friction when it is sliding. Friction when it is sliding, uh, which is more than the amount of friction needed to overcome micro sliding, which is more than that required to overcome sticking. And the stiffness of the machine greatly affects the amount of force transmitted to the bonding interface. These were all the machine parameters or the process parameters. But then, depending on the type of material that is being fused, we also have several material parameters that can decide the outcome of the build process. The surface topography for one affects the initial contact area between the two surfaces through the contact of asperities, and it therefore influences the frictional and normal stresses at the interface. The presence of surface contaminants and oxides can prevent metal to metal contact, and they must be broken up and displayed in order for our diffusion bonding to begin. Stiffness, that is the geometry and modulus of the substrate, directly influence the resistive force produced by friction at the bonding interface. The hardness directly influences the coefficient of friction between the two metals, and empirically, it has also been shown to influence the amount of energy required to form a bond. A very interesting application of the ultrasonic consolidation process is captured in this slide, where it enables the fabrication of smart structures, where the integration of sensors, actuators, or even reinforcement fibers within a single metal matrix, and thus can be used to come up with multifunctional parts. Some researchers have also incorporated channels for fibers using laser beam melting. And such an example is shown here where these fibers are say coming from the back and emerging from this side, and they have been well preserved because we can see the light signals coming out of it, which means that they're not damaged. Another powerful advantage of the ultrasonic consolidation process is its ability to actually combine multi-materials which need not be metallurgically compatible. Since it is a solid state process, the materials do not really melt and mix, and thus the formation of any deleterious secondary phases is prevented, making it a truly multi-material process. Here we have a simplified process modeling workflow for the ultrasonic consolidation process. On the bottom right here, we have a free body diagram of what is the current sheet and the pre-deposited layers. The force given by the sonotrode is denoted by P. Fs is the frictional force at the sonotrode and foil interface. Fa is the frictional force at the say pre-deposited layer and base plate interface, and we separate these two in the diagram to the left. Fi is the internal frictional force. Now the motion of the sonotrode itself, which delivers the ultrasonic vibrations, can be written as some sinusoidal function, in this case given as dt equals d naught sine 2 pi ft. The velocity and acceleration of the sonotrode can be found just by differentiating this displacement with respect to time, as shown here. Vt equals 2 pi f d naught cosine of 2 pi ft, and acceleration being equal to minus 4 pi square f square d naught sine 2 pi ft. The equation of motion of the top surface can be written as Fs plus Fi equals ma, where Fs is the friction force between the sonotrode and the strip, equal to mu times p. Mu is the coefficient of static friction. The reason it is static is because A, static friction will typically be higher, and so it can provide a limiting value, and B, no relative motion is desirable between the sonotrode and the sheet being deposited in the present layer, and so the friction would be static in nature. Its direction is opposite to the velocity of the sonotrode. The mass of strip in contact with sonotrode M is obtained as LCWTS rho, where LC is the contact length between the strip and the base, W is the width of the strip, and TS is the thickness of the strip, rho being the density. Then the contact length between the two materials 1 and 2 in contact, and we obtained as shown here. Once the interfacial shear force is known, one can find out the energy input in each cycle, because we know that power is equal to force times velocity, which is a formula which we might have used during our 11th and 12th, and we integrate this power over some time interval to obtain the total energy, which is what is also shown here. Further, the dwell time at a given point can also be calculated as the ratio of the contact length to the traverse velocity. The number of motion cycles when the sonotrode is above the contact area can also be calculated, and hence we can have the total energy supplied to at any given point. The process itself offers several advantages, such as it allows the embedding of temperature and pressure sensitive objects into the solid metal matrices, such as silicon carbide fibers, shape memory alloy fibers, optical fibers, fiber Bragg gratings, electronic sensors, etc. It is permitted due to the low temperature, high plastic flow of the metal matrix. It is encountered during ultrasonic consolidation. No atmospheric control is needed due to the solid state room temperature nature of the process. There are no particular safety hazards associated with the formation of liquid metal, uh, metal fumes, powder handling, and so on. Further, due to the absence of liquid to solid transformation, ultrasonic consolidation also minimizes the residual part stresses and net shape distortion when compared to fusion-based processes. The deposition rates in this case are far higher than many layer manufacturing processes due to a far larger deposition spot size, which is equal to the width of the layer itself, and the lack of any lengthy post-processing procedures, because as we saw, a milling operation will do the post-processing for each layer. It can be used to bond materials that are metallurgically incompatible, as we just saw, such as aluminum, titanium, copper with stainless steel, and so on. And it is a highly energy efficient process, consuming as little as 5% of the energy required for more conventional welding processes. So with that, we have completed the recapitulation of this week's lecture. We'll break for a short while now, and when we come back, we'll continue with solving some example assignment problems. Welcome back. And now let us look at a few questions, which will be similar to the assignment questions posed to you, and will help in strengthening our concepts and solving these problems. The first question is, which of the following materials cannot be processed by a sheet additive manufacturing process? The options given to us are aluminum 6000 series, copper, aluminum 7000 series, or whether all of them can be processed. Now, in the context of sheet additive manufacturing process, what we saw is that most of the time they are solid state processes, and thus they're amenable to the say processing of metallic materials, even aluminum and copper. In fact, they may also be used to join some of these multi-materials or multi-metals together, which may be otherwise metallurgically incompatible. It can be used for processing aluminum 6000 series, copper, as well as aluminum 7000 series, and thus all of the above can be processed. The second question is asking is, the amount of ultrasonic energy delivered is directly proportional to amplitude of ultrasonic vibration. Then, can we use an arbitrarily high value of amplitude for ultrasonic consolidation? And several assertions and reasoning are given to us. So, yes, because the speed of travel scales linearly with the vibration amplitude. If we have a higher amplitude, we can weld faster and thus finish the building process faster. No, because the process approaches linear friction welding. No, because it can lead to cracking. And no, because a very high energy input can lead to melting of the feedstock. Let us examine all of these options one by one. First, it is not true that the speed of travel scales linear with vibration amplitude, and even if it were so, that is not reason enough to increase the amplitude arbitrarily. Second, uh, even if the process approaches linear friction welding, that is not really an issue. However, the use of very high amplitudes can indeed lead to cracking, and thus we should not arbitrarily switch to very high amplitudes. And a very high energy input can lead to melting of the feedstock. Typically, we would like to restrict ourselves to within 30 to 50% of the melting temperatures and remain in the solid state. So options C and D are right. And that's why, as we saw in the slides, typically vibration amplitudes between 5 to 40 micrometers are used in this process. The third question is asking us, which of the following regions are subjected to relative motion in an ultrasonic consolidation process? Is it the sonotrode sheet interface in the welding direction? Is it the sheet-sheet interface between new layer and previously bonded layer? Is it the interface between two previously bonded sheets? Or is it the sonotrode sheet interface in the transverse direction? Let us just draw a quick schematic which will help us identify all of these interfaces. This is my sonotrode. This is the material being welded in the current step, and if this is the pre-deposited layer. So the pre-deposited part, which will of course consist of multiple layers, and then we will have the build plate of the angle. The sonotrode sheet interface will be located here. This is option A. The sheet interface between new layer and previously deposited layer is here. The interface between two previously bonded sheets is say somewhere here, and the sonotrode sheet interface in the transverse direction if we were to draw a front view of this, this interface right here. And we are asked which of the following regions are subjected to relative motion. So we know that uh, the sonotode sheet interface in the welding direction will have relative motion because this will rotate and move forward, and so there will be a relative motion, so A is correct. The sheet interface between new layer and previously bonded layer is also needed because here we need to break up the oxide layer and expose the pure metal surfaces for diffusion bonding. The interface between two previously bonded sheets, such as one shown in C, should not undergo relative motion because it will lead to, you know, uh, say destruction of the already bonded layers. So this is undesirable. And D, the sonotode sheet interface in the transverse direction again should not undergo relative motion because we introduced knurling patterns on the sonotode surface so that it grips the top surface of the sheet really well, and the sheet being printed in the current layer moves along with the sonotode. So any sort of relative motion here is again undesirable. So options A and B are correct. Question 4 is asking us, what is the Blaha effect? Is it that the flow stress decreases when an oscillatory stress is superimposed to a deforming specimen? Does the flow stress increase when an oscillatory stress is superimposed to a deforming specimen? Does the flow stress decrease when a constant stress is superimposed to a deforming specimen? Or does the flow stress remain unchanged when an oscillatory stress is superimposed to a deforming specimen? Two things are being talked about in each question. First is the stress, type of stress, whether it's oscillatory or whether it is constant. Second is the what happens to the flow stress or the effect of this stress. Whether it increases, decreases, or remains unchanged. The flow stress remains unchanged when an oscillatory stress is superimposed to the deforming specimen. This is clearly not correct, else we would not have been using this process in the first place. Why do you superimpose an oscillatory stress if it does not change anything? The flow stress decreases when a constant stress is superimposed to a deforming specimen, but then in the case of ultrasonic consolidation, we are not using a constant stress but an oscillatory stress. The flow stress increases when an oscillatory stress is superimposed to a deforming specimen. This would have made our lives harder, and so it is not really desirable. And the Blaha effect, which is a beneficial effect, actually says that the flow stress decreases when an oscillatory stress is superimposed, and hence option A is correct. As we saw in the slides, the Blaha effect is also called acoustic softening because essentially it is softening the material uh, by the application of vibrations or acoustics. The fifth question is asking us, which step determines the productivity rate in cubic technologies LOM? Is it grid cutting, outer contour cutting, sheet indexing time, or decubing operation? Let us just try to compare the times taken for each of these steps. Say if I denote the time for grid cutting by TA, for outer contour cutting by TB, for sheet indexing by TC and for decubing by TD. The indexing time will be the least because it's very quick. The outer contour cutting is expected to take more time than indexing, but of course they will be comparable. It may even be smaller in some cases if the contour is very simple or very small, but typically it will be slightly greater than the indexing time, but smaller than the grid cutting time, which is expected to take uh, comparatively more time than the outer grid cutting. But all of these are far smaller than the decubing time, which will be in several hours. As we know, the productivity rate for any process is determined by the slowest step, which in this case is the decubing operation, and so option C is correct. Option D is correct. In question 6, we are asked to find the ratio of time taken for grid cutting to the time taken for scanning the outer contour for the given geometry, which is a very simple geometry made of simple squares, but it will give us some idea of the scales for decubing time and for uh, contour scanning times. Now, as we saw in the slide, typically the processes which go on in each built layer are, say, first the parting cut is taken to separate the region of interest in this layer from the overall sheet. Then we'll cut the contours. We may have exterior contours and interior contours, and then we'll scan the grid lines. We're asked to find the time taken for grid cutting and outer contour. So let us start by finding the time taken for grid cutting. What is that time? For grid cutting, we'll have to scan say all of these lines, and since nothing specific is being told about the parting cut, we can take that as part of grid cutting as well. Essentially, what we'll be scanning are these lines that I'm now highlighting in red. If we go row wise,
Do not disturb. Activated.
and also the same lines column wise. So we can just multiply it by 2. So this grid cutting time, as we know, is proportional to the surface area, not the volume. So it's proportional to twice, once along the rows, once along the columns. 4 times capital A, because we scan this length of capital A 4 times. 1, 2, 3, and 4. Plus this smaller distance, which is this pixel length A, which was say 1, 2, 3, 4, and 5. Similarly, on the other side, 6, 7, 8, 9, and 10. This is 10 times 2 into small a. What we can also see is that capital A and small a are related. Here we have 1, 2, 3, 4, 5, 6, 7, 8. Capital A is equal to 8 times small a. Therefore, Tg is proportional to Tg is proportional to 8 4s are 32 plus 20 52 into 2 104 times small a. Let us also find the time taken for scanning the outer contour. What is TC? TC in this case is just the bold line corresponding to this square, which I am now highlighting in green. This time simply is proportional to 4 times capital D, but capital D is again related to small d as 1, 2, 3, 4, 4a. So TC is proportional to 4 into 4a or 16a. We're asked to find the ratio between time taken for grid cutting and for outer contour, or Tg by Tc. Assuming that they are related by the same constant of proportionality, this will simply be equal to 104a by 16a, which is equal to 13 by 2 or 6.5. And thus we see that the time taken for grid cutting is actually 6.5 times the time taken for scanning the contour. That is why it is said that the grid cutting time is the longest scanning time, and the decubing time is even far more. The seventh question is asking us, what are the advantages of Kira's paper lamination technology when compared with cubic technology alone? Does it give higher strength? Does it prevent distortion and curling? Are there no fire hazards associated? And does it introduce minimal internal strains? We did see that the parts made from Kira's paper lamination technology are 25% harder than equivalent wood. Because of the use of flat hot plates, no distortions and curlings are introduced. Since it uses a mechanical knife instead of a laser, there are no fire hazards associated. Further, because it's a solid state process, there are minimal internal strains. So all 4 options are correct in this case. Question 8 is asking us, what is the primary advantage of sheet additive manufacturing process compared to other AM processes? Is it the lack of adaptive slicing? Is it the lack of materials library that can be processed? Is it the higher energy requirements? Or is it the comparatively greater hazard to health and human safety? Lack of adaptive slicing is indeed true, because here we saw that in this case, the layer height was equal to the uh, uh, thickness of the sheet feedstock which was being used, which would still be, say, in several hundreds of micrometers. But the problem is that we cannot adapt it to, say, better approximate a region of high curvatures, for instance. The library of materials which can be processed using the ultrasonic consolidation process is fairly large. And as we also saw, I think in one of the slides, it can be used to process a large variety of materials which may even be metallurgically incompatible, because it is a solid state process. And since the materials are not melting and mixing, no deleterious secondary phases will form. So it is not really limited in terms of the materials that can process. Also, what we saw is that across the different types of sheet additive manufacturing processes, we can print paper, we can print ceramics, we can print plastic, we can print metals, and even a few other things. So it is not really limited in terms of the library of materials that can be processed. Just a reminder that we are looking at disadvantages. Does it have higher energy requirements compared to other additive manufacturing processes? The energy requirements uh, actually are far smaller. I think in the case of ultrasonic consolidation, we also saw that they're estimated to be only 5% of the energy required for conventional fusion welding based processes. The energy requirement for other uh, sheet additive manufacturing processes can also be assumed to be of similar range. And so higher energy requirement is not really associated with it. And what about the hazard to health and safety? There are a few processes such as cubic technologies, laminated object manufacturing, where indeed, with the use of CO2 lasers, we have some smoke coming out, which needs a proper exhaust. And in other processes where we use mechanical knives, we don't have smokes or fumes. Uh, some processes might involve sintering, but even then, some of the common hazards, such as lasers, which require proper handling and laser safety, laser glasses and closed chambers, and so on, or the use of powder feedstock, which are very dangerous for human health and should not be inhaled, and thus require careful containment, cleaning, uh, proper handling and disposal, or even liquid resins, which in some cases may be toxic to humans. None of these factors are there. And so, compared to other additive manufacturing processes, the sheet AM processes, in fact, are less hazardous to health and human safety. Thus, what we can say that for the among the options given to us, the lack of adaptive slicing is the only primary disadvantage of the sheet additive manufacturing process compared to other AM processes. And that is all that I had planned for this week. Uh, okay, I finished on time. It's just 8. So thanks for tuning in to this week of the live sessions for the course on Fundamentals Additive Manufacturing Technologies. I am Sourav Goswami from IIT Bombay, and I hope to see you all again in the next session. Thank you.